I think what I want to do is use my whiteboard here and it'll be easier. There's so much to write on these problems that I need more space
Okay.
than I get in writing there. First of all, let's try to draw a little picture of this so we have reference for it. I'm going to try to write small. It is not easy for me. Okay, so mark there, mark there. That is y equal sine x. And this is y equal cosine x. And they have asked us to take the portion from 0 to pi over 4, which is right there. Remember, that's where sine of pi over 4 equals cosine of pi over 4, right? And let's move that one out of the way so I can put this distance in there, which is square root of 2 over 2. Are you with me?
Yep.
Okay, let's move that up a little bit higher, so I'll put 1 up there. Okay, and so it's asking us to take this area right here and reflect it both around the x-axis and also around the y-axis.
Mm-hmm.
Okay, so let's talk about 6a. What are we going to use to reflect that, to revolve it about the x-axis? What method are we going to use to find the volume? We're going to use washers or discs?
Washers.
Yeah, the way I kind of tend to look at these is, does it leave a hole? Does it leave a convex hole in the object that gets created?
Mm-hmm.
And clearly it does. I mean, if I draw the other end of this, it's going to look something like that. And there's this area, yeah, here if I point, there's this area right here that represents the hole. So we're definitely going to use washers. So, and the formula when you're using washers for volume is what?
V equals pi times the integral of big Rx squared minus little Rx squared.
Dx.
Dx.
Okay. So we have our discs that I'm going to represent by that blue line.
Right.
What is the outside radius?
Cosine x.
So we're going to square it. It's the inside radius.
Sine x.
And we're going to go from what to what?
0 to pi over 4.
Now, this is a little trickier interval to solve than it looks, or integral. We could certainly say that it's the integral of cosine squared minus the integral of sine squared. But believe it or not, those aren't easy to find.
Mhm.
You haven't gotten to the section yet on how you take integrals of trig functions like, oh, they call it this, sine to the m times cosine to the n. There's a method of doing those, and it would cover these. But that's the next method of integration you'll probably learn the next calculus course you take.
Okay.
But there's an easier way to do this. What's the identity for that?
I'm not sure, actually.
Okay. Surprisingly, you have to actually be better at trig when you take calculus than you do when you took trig. But if you remember back to your trig, that's the cosine of the double angle for that. In other words, cosine squared minus sine squared is equal to cosine of 2x.
Okay.
Okay? And then this actually becomes relatively easy to integrate. What's the integral of cosine of 2x?
Um, 1/2 sine 2x.
Yeah. Sine 2x. I always do it like this. I take the integral and then I divide it by the derivative of the inside.
Right.
Always easy to check because if you take the derivative of sine 2x over 2, you get cosine 2x.
Right.
We're going to evaluate that from 0 to pi over 4. And don't forget our leading pi. It's easy to do that when you take the constants or pi out of the integral sign.
Mm-hmm.
And if we evaluate this, I think we get, let's see, if I go over here, we get pi times sine of pi over 2, which is 1, minus 0. So the volume is pi over 2. Do you see how I did that? If you have any questions, bring it up now.
Yeah, I saw how you did it.
Okay, cool. All right, so that's 6A. 6B, a little trickier. They want us to revolve it around the y-axis. So we're not going to make this shape at all. In fact, let me erase that blue line because we're going to have that line be vertical to the y-axis. In other words, we're going to make what would look like a top, right?
Right.
Okay. So again, well, what are we going to use? Washers or discs?
Well, wouldn't the integral be in terms of y, so 0 to 1 instead of 0 to pi over 4?
We'll get to that.
Okay.
But in seeing the object that is going to be created, going to be a solid object like that.
Yeah, it's going to be
Require washers or discs?
discs.
Correct. We're not going to create anything that is a hole. In other words, there's no hole in the middle.
Right.
So we're going to use discs. And the radius, here, let me draw that a little bit higher up. The radius is what right there?
Cosine x.
That's the y value.
Oh, pi over 4.
Here's our equation. Y equal, at where I've drawn the yellow line, y equals cosine x. But remember, our skinny dimension is along the y-axis. So our integral is going to be dy, which means our function has to be a function of y. What we're looking at here is a function of x.
Right.
So let's solve it for x. What is x equal to? Let's go back a second. If I tell you the cosine, I tell you the sine of 30 degrees equals 1/2, then how do you solve for 30 degrees? What's 30 degrees equal?
30 degrees equals pi over 6.
The inverse sine of 1/2. In other words, what I started with was the sine of x equals y. And if I want to solve for x, x equals the inverse sine of y. And now I have my function as a function of y, not x. And that's the key in this step, is you have to solve for x. Because that dimension that we're looking at, that yellow line, is the distance to x, right?
Right.
Okay. So, our volume is going to equal, oh, there's something else strange about this. Really, we should start from the bottom. Let's start from the y equals 0 line. So we're going to go from 0 to what?
To 1.
Well, the problem with that is from 0 to root 2 over 2, x is the inverse sine of y. That's from 0 to root 2 over 2. But from root 2 over 2 to 1, x is the inverse cosine of y.
So do we split up the integral into two separate integrals?
Yeah.
And integrate from 0?
From 0 to root 2 over 2.
And with the pi out front of the volume, you only multiply it by one of the integrals or both?
Just a second. With the pi outside, there is no pi yet. Hold on a second. So that's the radius. God, I guess we have to square that too, huh? So each disk is going to have a volume of pi r squared, and r is x, which is inverse sine of y.
Mm-hmm.
All right. I forgot to square it when I did it. It's going to make it marginally more difficult to solve. What method? Oh, here, let me put the other one. Plus the integral of pi from root 2 over 2 to 1 of the inverse cosine of y squared. dy. So that's what we have to do, right?
Right.
What method are we going to use to solve these integrals? Think
The
last session we had u substitution, we had parts, we had partial fractions. What are we going to use?
arctan or arc
You know,
sine.
oddly enough, that was my first inclination too, and I spent a whole half a page doing it incorrectly. Remember we had a problem that was this. How did we do that one? Hint.
Lipit, u substitution.
Well,
Or here's my parts.
by parts, exactly. So that's how we're going to do these, I think. First time I did it, I didn't square it, and this was easy to do. Might be a little harder to do with it squared, but let's find out. So to do this integral, basically going to end up with uv minus the integral of v du. So we need a u and we need a dv. What's u going to be equal to?
Sine, inverse sine.
Yeah. Question is, what do we want to do with that squared part? Whoops. Don't do that yet. So du, which we have to solve for, dy equals
2 sine inverse sine y.
times what? Times the derivative of the inside. In other words, all we're doing here is using the chain rule.
So I don't know what the derivative of inverse sine is.
Well, I'll bet you do. What is the rest of it?
Oh, 1 over root 1 minus y squared.
So that is du. Move the dy over there. And now u times v. Well, let's see. If dv equals everything else, then dv equals, we're talking up here, that's dy. So v equals y. Now we're ready to write our integral. And we may end up with, no, I don't know, man. This makes it a lot harder when you have to square it, I think. We may have an iteration here, which I hope we don't, because then I'll have to erase this whole page. Let's see, uv is what? It's y. I'm going to really start writing smaller. Y times inverse sine of y squared. That's uv. Minus the integral of v, which is y, times du. Now let's take that 2 out. Let's leave that in. Yeah, I can see what's going to happen here, I think. Now, again, we have a combination of things. Ooh. In other words, whenever you see a product of two different type of functions, you got to think integration by parts.
Right.
And the second iteration should get rid of this. Wow. Yeah, I think it will. I'm going to erase enough of this. Now you'll get a recording of this if you want to go over the specifics.
Okay.
I'm going to leave that part there because we haven't done that part yet. Let's see. So now that is what the integral was equal to that. Once I get this to a point where I'm sure you can take over, then we'll go on to the next problem. But at this point, these are hard enough that it's not at all clear how to proceed. Okay, so now we have this. The original integral that we were trying to solve is equal to this. So now we have to solve this integral. So let me start at the top. 2 integral of y inverse sine of y all over root 1 minus y squared dy. We just had the inverse sine. We know how to do that, right?
Right.
Integration by parts, one iteration takes care of it.
Mm-hmm.
We got this other stuff, y over 1 minus y squared.
Right.
How are we going to do that? That's, first of all, a polynomial. So when we're trying to figure out what our u is going to be, it's going to, again, based on Lipit, it's going to be that. And our dv is going to be y over square root of 1 minus y squared dy, everything else.
Mm-hmm.
Now, how are you going to do this integration on the left to solve for v?
Use substitution.
Beautiful. It's not inverse trig function. It would be if there was no y in the numerator, if that was a 1. But since there's a y in the numerator, which is the same power degree as the derivative of what we're going to let this be,
Mm-hmm.
then we're going to be able to solve for v. Okay? Now, once you have v, if we go over to the right side, I'm not going to take the time to do it just because it's so much work, and I think you'd be better served if we have a little bit of chance to look at number 7.
Okay.
I don't know. But let's see. We know we always have to take the derivative of this, and we have to integrate the thing on the left. So the derivative of that is 1 over square root of 1 minus y squared dy. Okay. So now, when we do our UV, our last UV, stay with me here, we're still taking this integral that we had up there.
Right.
Okay. And it's now equal to UV minus the integral of v du. But we have a new UV. U is inverse sine and V is going to be whatever we get when we go through all of that. We'll call that Z. for purposes now. That's not the hard part of this problem. You know how to do U substitution.
Yeah.
Now the question is can we get rid of this last integral sign? Well, this is v du. Wow, shoot. Without solving for v, can't do it. In other words, we'd have to take another 5 minutes to solve for v, and we're going to have something in there, but it's all going to be polynomial. Notice we will no longer have an inverse trig function. It'll be z. We called v equals z just because it's some z, but we know that z is a polynomial.
Mm-hmm.
And it's going to be over this. dy over square root of 1 minus y squared. Now you're going to have some polynomial in the numerator, some in the denominator, and assuming we can integrate that, we're done with the integral sign and we have an answer.
Right.
All right. Let's go to number 7, which is actually relatively easy. Although the integration, yeah, I think it is relatively easy. If I draw a quick I graph that function in Wolfram alpha. You familiar with Wolfram alpha?
No, I use Desmos usually.
I'm familiar with Desmos also. I'm not sure which is easier. Desmos is just a calculator, right?
Yeah, you can. It's a graphing calculator that you can put in.
Okay. The beauty, I don't know if Desmos does this. I've used it, but I don't remember. The beauty of Wolfram alpha is it's difficult to put in these functions, making sure you get all your parentheses in the right place.
Right.
So the fact that they tell you what your input is very helpful. Because if you're missing a parenthesis, they'll give you the wrong function. But this is our function, is it not? Or did I get it wrong? Is it x cubed?
It's 1/10 x squared root 3 minus x.
So I got it right.
Yep.
Okay, and that's the graph of it. Okay.
Right.
So let me close this out and go back to here and draw an approximation of that. If we start to go over and you got to go, tell me and I'll stop. But otherwise, I'll try to get a little bit of this explained.
Okay. I'll have to leave at 10:30 just to get back to school.
Okay, well, that's just a couple minutes, so I'll be really quick here.
Okay.
Okay, so this thing is being integrated. If you do the math, you know those 2 points are there. So it's going to be the integral from 0 to 3. We're going to use disks, not washers.
Right.
We're going to revolve around the x-axis. So this becomes the integral. I'm going to take the pi out. And this is the function. Ooh, it's x squared. I even wrote it in here wrong.
Can we take the 1/10 out since it's a constant?
No, we can't. It's inside the parentheses being squared.
Okay.
Well, our next step is to square that. Okay, I can square 1/10, becomes 1/100th. I can square x squared, that becomes x to the 4th. And I can square this, which becomes 3 minus x. With me?
Yep.
Now we can take that out. Distribute. We got 3x to the fourth minus x to the fifth. That's going to be very simple to integrate.
Right.
I'm not sure this problem is the easiest of the bunch. And the answer, they said, use units, cubic meters. Any volume is always cubic. So you know how to do the rest of this.
Yeah.
And that should do it. Yeah, that 6B was the toughest one.
Yeah, yeah.
We could have spent the whole half hour working that through, but I think you understand how to do it now.
Yes.
Hopefully the polynomial that results is an integratable polynomial. I don't think they'd give it to you if it wasn't. Although, do they allow you to use your calculator on these at all? Or you have to do all these manually?
I'm guessing these were supposed to just be manual, but if that problem showed up on a test, it would definitely be a calculator problem.
I would. It depends on what that polynomial comes out to be after using U substitution. It might be something like square root of 1 minus y squared, in which case it would cancel with the bottom and you'd just be taking the integral of 1 or something like that.
Yeah, our teacher usually doesn't give us problems that we have to integrate, like integration by parts, do it more than twice. So
yeah, that would be cruel to make you do it more than that. Unless they taught you there is a method, like if you have to do 8 iterations, there's a table you can use to get from step 1 to step 8 instantly. Differentiate everything on the right side, integrate everything on the left side. It's something like that. But so anyway, hopefully this was helpful to you. John, have a good rest of your school day. And I'll talk to you. We have a session on Saturday or Sunday.
Yeah, Saturday at 2:30.
And it's extremely helpful that you sent this in advance, because otherwise I'd have had to spend the whole half hour working it out myself, and that's not in your best interest. I'd rather spend the half hour before our session working it out, so I know how to explain it better to you.
Right. I'll send some more problems on Saturday morning.
Sounds good. Talk to you then. Bye-bye.
Bye.